Okay, so we're still going to be talking about determining convergence for series of constants. Again, our end goal is still going to be to figure out if, for our intervals of convergence, if we're convergent or divergent at those endpoints. What we're going to be talking about today are our comparison tests. For the comparison test, we're going to be comparing to our two favorite series. So let's just talk about what series we have so far, or what series tests we have so far. Okay, so just to recap, we have our geometric series, our p-series, our nth term test for divergence, and our integral test. Okay, so which are our two favorite series? Which are the easiest to just, you look at, you know it's convergent or divergent? These guys. These guys are our, nope, that's too much. These guys are our favorite series because we could just look at them and we know convergence or divergence, okay? So when we do comparisons, we're going to see that we have series that are very similar to either a geometric series or very similar to a p-series. Our gut instinct is going to tell us that because it's so similar to these series, it's either going to also converge or also diverge, and we can do a little bit of a comparison to make that assessment. Let's look at an example and we'll kind of get an idea and then we'll move from there. Okay, so I want to decide if this series is convergent or divergent. I have the sum of 1 over 2 to the n plus 1, okay? And I just want to remark that this is very similar. First of all, it's not a geometric series, okay? It would be a geometric series if I had just a number times another number to a power. It'd have to be a r to the n. Okay, so this is my form for a geoseries, and because of this plus 1 in the denominator, it's not a geoseries, but it's very, very, very similar to a geoseries. Okay, if I didn't have that plus 1 in the denominator, if I just had the sum of 1 over 2 to the n, that would be a geometric series, okay, because now I have n only as an exponent, nothing's being added or subtracted, now I have a geometric series. And I know that this series is the same as this series, which is very plain to see, is a convergent geometric series with absolute value of r equal to 1/2, which is less than 1, okay, which is why I'm convergent. So again, my gut instinct tells me that because I'm so similar to a convergent geometric series, I should also be convergent, but I want to prove it some way, okay? And you're gonna love the comparison test because it's very straightforward, it's very easy. And what I can say is that there's a relationship between the terms of this series and the terms of this series. Okay, I want to know what that relationship is. So what's the relationship between the terms of the series that I want to know about and the terms of this other series that I know to be convergent? So pause it, think about it, and decide, is the first one less than the other one? Is the first one bigger than the second one? Are they equal? Think about it and come back. Okay, and 1 over 2n plus 1 is less than 1 over 2n. I don't know why I'm saying 2n. 1 over 2 to the n plus 1 is less than 1 over 2 to the n, right? Because my denominator is bigger, which makes my quotient smaller. So now if I have a series that's convergent, and essentially the whole idea of convergent, it means that I'm adding on infinitely many terms, but yet I'm getting a finite value. So my terms are small enough that I'm getting a finite number. I have a new series where the terms are even smaller. Okay, and if the terms of this series are small enough to converge, and my terms of the series that I'm interested in are even smaller, then that would follow that my series is also convergent. Okay? Okay, so again, because the terms of my series are even smaller than the terms of a series I know to be convergent, it makes sense for this new series to also converge. Okay, the only thing that I would need for housekeeping is to state that this relationship up here is true for all n values on the interval that I'm looking at, and I don't indicate, so I'm looking from n equals 1 to infinity. Okay, so I'm stating that this relationship is true on the interval that I'm looking at, so for n greater than or equal to 1, and I also just need to say that I'm doing a direct comparison test, okay? Okay, and with those two little details, I can now say that my new series also converges, okay? Let's just write out the rules for the direct comparison test. Okay, so the direct comparison test is comparing two series, the sum of the a sub n's and the sum of the b sub n's, and we want our series to have positive terms, and the main reason for that is so that we can make a quantitative assessment and the relationship between those two series. But if we should come up with a series with negative terms, we can, as long as they're not alternating. Alternating is a totally different ballgame. But if we have a series that has negative terms, we just pull that negative out front as a coefficient, and then we have a series with positive terms. So, okay. So, if the sum of the b sub n's is convergent, what relationship would I need to have between my a sub n terms and my b sub n terms in order to make the sum of the a sub n's to also be convergent, in order to force that. So I really want you to think about that. So I have a convergent series, and I want to know that for certain that my series that I'm comparing it to is also convergent. So what relationship would I need to have? Pause and come back to me. Okay, the relationship that I need is that my a sub n's need to be less than or equal to b sub n in order to have another convergent series. Okay, so what I like in this too is that I have a magic door, and you don't know how big the door is. Okay, but it's a door, so we don't know how big it is though. Okay, so I have my magic door, and convergence means that we can fit through the door. Divergence means that we cannot fit through the door. Okay, so I know that if... Okay, so you don't know how big this door is, but what you do know is that Kevin Durant can fit through that door, and that's a tall man. Okay, so if Kevin Durant can fit through the door, and you're smaller than Kevin Durant, you're all smaller than Kevin Durant, everybody's smaller than Kevin Durant, can you fit through the door? The answer is yes. And that's what this direct comparison, this part of the direct comparison test says. So if Kevin Durant can fit, then so can you. Okay, so if I'm smaller than convergent, then I also have to be convergent. Okay. The second part of this says, so the second part says that if the sum of the b sub n's is divergent, what relationship would I need to have between my two series in order to know for a fact that my other series is also divergent? Okay, so think about this, and if it's helpful, think about the door again. Okay, so I have a series that's too big to fit through the door. Okay, what would need to be the relationship between my series that I'm trying to find out about and this series in order to know that my series that I'm trying to find out about is also divergent? So pause and come back to me when you figured it out. Okay, in this situation, I would need my a sub n's to be greater than or equal to my b sub n's. All right, so that's the situation that if you don't fit, what do you know about Kevin Durant? Kevin Durant is not fitting through that door. Okay, so the magic door, we don't know what it looks like, we don't know how big it is, but you're not fitting, Kevin Durant's not fitting. Okay, and that's our direct comparison test. So let's look at some examples. Okay, we want to know convergent or divergent. I have the sum of 5 over 2n squared plus 4n plus 3. Okay, and just to go through again, is this geometric? Nope, not geometric. Is it a p-series? Nope, it's not a p-series. Will nth term test do anything for me? Nope, nth term test is going to fail me. I'll get 0 for my limit. Okay, so I'm going to try a direct comparison test. When you're trying to decide what to compare to, you just are going to do the key term from the numerator divided by the key term from the denominator. So the key term from the numerator, well, why don't you pause and think about what the key term over the key term would be, and then come back. Okay, so I'm going to compare it to the sum of the key term from the numerator would just be 5, and the key term from the denominator would be 2n squared. Okay, and once you do this, you should either have a geometric series or a p-series, okay, that you're comparing to. So is this series geometric or is it a p-series? Pause, tell me if it's a p-series or a geo-series and whether or not it converges or diverges and why you know that, and then come back. Okay, so this is a p-series. P is 2. Okay, what's remarkable about that? Well, we want our p-value to be greater than 1 in order to be convergent, so since p is 2 here, we are, in fact, greater than 1, and because it's greater than 1, I'm going to be convergent. Okay, so once we establish what we're comparing it to and whether or not that series is convergent or divergent and why, we need to make a comparison between our two series. So I need to make some kind of assessment between the general term of this and the general term of what I'm comparing it to. So I want to know what the relationship is between the general term of my series that I'm interested in, my 5 over 2n squared plus 4n plus 3, and the general term of the series that I know about, which is my convergent p-series. So this is what I need to answer. Figure out what kind of, if that's a less than or a greater than in that place of that question mark. Pause and come back. And you should establish that because the denominator of the left side is bigger than the denominator on the right side, but the numerators are the same, then the left side is less than. Okay, the denominator is bigger, the quotient is smaller, so the first one is less than the second one. Okay, so I am smaller than a convergent series. What does that mean? Okay, what does smaller than convergent mean? That means that Kevin Durant can fit through the door. Can I fit through the door? Yeah, I can. Okay, so smaller than convergent means also convergent. Love the direct comparison test. Let's do another. Is this one convergent or divergent? The sum of square root n over n minus 1. All right, just going through, is it geometric? Is it a p-series? Does nth term test work? Ask yourselves those questions. And the answer to all those questions is nope. Okay, it's not geometric, it's not a p-series, nth term test, I'm going to get 0, so the test fails. And we don't do integral tests unless we actually have to, so my next choice would be a direct comparison test. Okay, and the way I start my direct comparison test, again, is to say that I'm comparing to the sum of the series of the key term over the key term, and then see what that leaves me. Okay, and if I do key term over key term, I'm comparing it to the sum of square root n over n, which isn't screaming a geoseries or a p-series to me just yet. But try to simplify this for me and see what you can come up with. See if you could make it either a geometric series or a p-series. So go ahead and pause, simplify, and come back. Okay, so it might actually be better if I wrote the numerator as n to the 1/2 and the denominator as n to the 1st, and then if I divide, I end up with an n to the 1/2 in my denominator. But this essentially simplifies to 1 over square root n, and if I just divide out, which I can write as the sum of 1 over n to the 1/2. And I don't know why it's so gargantuan, but it won't let me shrink it any more than that. So, okay, so that's that series. So now is this geometric or is it a p-series? It's a p-series. Tell me more about it. Is it convergent or divergent, and how do you know? So pause, do that, and come back. Okay, it's a p-series with p equal to 1/2, which is less than 1, so therefore I am divergent. Okay, and just like the last one, once I've established what I'm comparing it to and whether that series is convergent or divergent and how I know it, I have to then make a comparison between the series that I want to know about and the series that I do know about. Okay, now I didn't say this in the last one, but you really want to make sure that you're comparing these two things. It's going to be easiest to make my comparison here. If I try to compare this with this, okay, my numerators are different, my denominators are different, I'm going to have to do a lot of algebra to make a good comparison. Okay, so you always want to do a comparison with the initial thing that you were looking at. So the question is, what is the relationship between these two general terms? Okay, and again, here my numerators are the same, but my denominator on this first one is smaller. Okay, and if the denominator is smaller, that makes the quotient larger. Okay, so what relationship do I have? I have that my series is bigger than the series that I know to be divergent. Okay, and again, if you were to make a comparison with this instead of with this, you'd have to do algebra instead of just being able to observe that, oh, the numerators are the same, the denominator on this one is smaller, which makes the quotient larger. Okay, so what does bigger than convergent mean? I misspoke. What does bigger than divergent mean? Think about it, pause, and come back when you know. Bigger than divergent means that I also have to be divergent. Okay, so I don't fit through the door. Kevin Durant is not fitting through that door. All right. Let's do one last example. Let's look at the sum of 1 over 2 to the n minus 1. Okay, so go through again. Is it geometric? Is it a p-series? Does nth term test work? Answer those questions, pause, and come back to me. Okay, so it's not a geoseries. It's not a p-series. The nth term test fails, so our next try is going to be a direct comparison test. So why don't you go ahead and try this, and then pause and come back to me. And I'm just going to give you guys the results when you come back. I'm going to compare to key term over key term, so 1 over 2 to the n, which, like I said before, is the same as the sum of 1/2 to the n, which is a convergent geometric series, with absolute value of r less than 1. Okay, so if that's the case, now I'm going to show my relationship between my two general terms here and here. And if I do that, what relationship do I have? Okay, if you haven't already figured that out, pause and come back to me. I can see here that my denominator is smaller, which is going to make the quotient larger. Okay, so now if I'm bigger than convergent, what does that tell me? Let's think about the door situation again, and if you need to pause, go ahead and do so. So bigger than convergent. I fit through the door. Kevin Durant is bigger than I am. Can Kevin Durant fit through the door? Think about that. And the answer is, I don't know, okay? The door could be perfectly me-sized, and then Kevin Durant can't fit. Or the door could be the size of the arch out front of the Colonial High School, and then Kevin Durant can for sure fit. Okay, so this means that I don't know.